Hi everybody, welcome back. We're on page 6 of your chapter 3 booklet, combining transformations. Fill an S in there, my apologies. So now we have two graphs. The first one here in the blue, you can see right here. And then the gray is right here. And that's the transform. So this one here we call, I've seen it called a couple different things, but we say it's the parent graph. Graph, or I've heard base function. This is the graph that we're going to be transforming. This is your y equals x squared. It's just your regular quadratic, right 1, up 1, right 2, up 4, etc. The second graph we have here, graph number 2, this is called a transformed quadratic function. So right now, we're going to state the transformations. We're going to list them based on here. So you'll notice it's negative in front. So remember, RST. So the negative out front, this indicates so the negative A value. So since A is less than 0, since A is less than 0, reflection over the x-axis or about the x-axis. I've seen it both ways. So that means that this here, it opens upward, now it opens downward. So anytime you have a negative at the very beginning on your A value, this indicates that it's a reflection about the x-axis. So the A value is less than 0. Your A value is greater than 2. So A being greater than 2, A is greater than 2. I apologize. I'll make that out right now. Sorry. So since A is greater than 2, the absolute value of that, so it doesn't matter the sign, we've already taken care of the sign in the reflection. All right, so we've already taken that right here in the reflection. Since the A value is greater than 2, this is a vertical stretch. So we've stretched it. You'll notice it becomes more narrow, like we saw in the other example. Right? And also, we have two transformations. We have a vertical transformation and a horizontal transformation. Notice the p value is 3. So p is equal to 3. Remember, it's the opposite sign. So if it's negative, we say it's 3. If it's subtract 3, we say it's 3. If it was plus 3, it would be negative 3. So p is equal to 3. So write 3. This is a horizontal translation. So there's our stretch, R and S, and our translation, so RST. Now remember, you could have up to 2 translations, and the next one is our Q value, or 1. So since we have Q equal to plus 1, we say, so that means up 1, this is because we're going up, vertical translation, RST. So in short, if you were listing these, this is our first time listing the transformations. So I've explained them all. We would say that this, oh, my apologies. We would say this is a reflection about the x-axis. So it opens downward instead of upward. A vertical stretch, and for short, VS, of 2. We don't say it's -2. The negative is represented by the reflection about the x-axis. That's the negative part. A horizontal translation of 3, we're going to write 3, and a vertical translation of 1, because we went up 1. And again, we can represent this with HT, and we can represent this with VT. It's just short, instead of writing those out all the time. Right? Vertical translation is VT. Just short. That. Your mapping notation is where you plug these values in. Your x and y will map onto x plus p, plus or minus a, because that's your vertical stretch, y plus q. All right? So this is how the points are transformed from one curve to another. So I'll recopy this, and then we'll add ours in. So we say our x and y, these are points based on your original function. So I'll talk a little bit more of these in the first example. And your p-value was equal to 3, so it would be x plus 3. Your a value was 2 when it was negative, so we say -2y. And the q value was up 1, so we play plus 1. You'll notice in the mapping notation, it's plus 3. I know the equation says -3, but it's the opposite sign because you're subtracting p, right? In the map notation, you add p, so that's why it's a different sign. This will help you map on your point-to-point here. We'll talk about a little more about this when we do an example. This is called mapping notation. I like mapping notation when I'm graphing by hand. It's an excellent way to graph a quadratic or any function. We'll do lots of different functions in Pre-Cal 12. But for now, in Pre-Cal 11, we just use this for our quadratics. So summary of what we've done to this point, our function can be represented as y equals a bracket x minus p squared plus q, or f of x equals a bracket x minus p squared plus q. A tells us what? As you guys remember, it tells us if the graph stretches or compresses, and whether or not, underline that, and whether or not it opens upward or downward. So the graph stretches if the a value is greater than 1. It compresses if the a value is between 0 and 1. If that a value is negative, it opens downward. If it's positive, it opens upward. Some of that we talked about already in Math 11. Remember, P and Q is representing the vertex. And it also, remember, we just learned today that the P value is your horizontal translation and the Q value is your vertical translation. Again, that's for vertex form. A maximum, we have a maximum is when the vertex, is the vertex when the graph opens downward. Underline, make it red. I'm going to steal this because the maximum is, or the minimum is similar. All we have to do is change down to up. So in the vertex of the graph, and then it opens upward. Your domain, as a lot of you are already aware, your domain is X is an element of the real number system. It goes on forever to the left and to the right. If you have a maximum value, that means your graph is going to go downward. So that is given by, and as you guys are aware, we've done this before, it would be y less than or equal to, I'm going to get my equation, so y less than or equal to, and it's your range, so it's whatever your q value is, right? Whatever the q value is. And if we have a minimum, that means the graph opens upward, so that means that it's your minimum y value. So that means that it's going to be y is greater than your q value, whatever your q value is, in vertex form. And the axis of symmetry, is given by x equal to p. It's whatever your p value is in your vertex, which is your x value, obviously. So x is equal to p of your vertex. So p and q represent your vertex. That is how we combine transformations. In the next video, we'll move on to page 7, where we're going to look at our first example using transformations. I hope everybody enjoyed the video, and we'll see you next time on page 7. Thank you.